Hi, everybody. We would like to start. First of all, thank you all for coming for this kind of a mid-event of the exhibition Learning the Grammar of the Act. It's an interactive live robotic painting installation. It's a collaborative work that's done together with the eDavid project here in the University of Konstanz, part of the computing department run by Professor Oliver Deussen. And it's closed my 10-month residency here as artist in residence in the University of Konstanz, looking and reflecting on different methods of how one can implement painting in relation to a contemporary and post-digital era today. The show is created with the very generous support of the Department of Visual Computing, with the Center of Cultural Foundation of Social Integration, the library, who gave us here the wonderful place and hosting us, and the support of all the university workshop and technical team. And of course, we have two individuals who help a lot, like Antonin Schulz, who created a certain kind of a program, a tracking program, and Markus Nebe, who helped to produce the video work. And now we're very honored to present our special guest, all the way from Goldsmith College in London, Dr. Frederic Leymarie and Daniel Berio from Goldsmith. They will present our current project about movement computing to model a class of visual production. Frederic is a leading researcher at Goldsmith University, specializing in AI, creativity, art, applied robotic, interactive scientific visualization. He's interested in understanding human intelligence in the context of embodied activities such as drawing, dancing, gesture, as well as combining visual perception with computational model to reveal how human gives meaning to objects and their environments. Our second guest is Daniel Berio. He's an artist, a programmer working between computer graphic, robotic, and graffiti art. He's currently finishing his PhD in Goldsmith University of London, where he's researching methods of the computational generation of graffiti and calligraphy arts through the simulation of movement and individual in their production. Please join us after the talk. We have some wine and some food for just unofficial gathering, and if you have any questions, the robot will be running there. Marvin Gülzow, that he's the PhD candidate from the University of Konstanz who supported the creation of the work here, programmed the robot, and he was a very important part of the creation of this entire work. So special thank you, Marvin, for this very intensive works over the last couple of months. And I will give the word now to our guest.
Thank you. Thank you. First, thanks to Professor Deussen for inviting us, and Liat and Marvin helping out. And we had the pleasure of having Liat and Marvin at Goldsmith recently. Gave us an excellent talk on the eDavid project in the context of painting. Today we'll specialize in a similar area, which is drawing and calligraphy. So I will give a first part of the talk. It will be more high level and more motivation, more about motivation. And we'll have two main hypotheses that we will pitch to you, and happy to take questions at the end and discuss further after that. So one main hypothesis, and Daniel will re-emphasize this aspect, is that movement is a key in evaluating the quality of a visual trace, and including the concept that it is the movement itself can be recovered from a static trace. So if you look at a finished product of a drawing, you can actually say quite a bit, which is fairly accurate, about how it was produced in terms of its movement profile. So here, this is just a bit slow. Let me try this. Here it is. Here's an example, trying to convince you. We'll have many examples during the presentation of a calligraphic symbol, and where we could start studying it and asking different people how do they think this was produced, and we would notice that they are fairly in agreement overall, and there are studies in this area from the world of psychophysics, and if you're interested we can refer to publications. The other main hypothesis we want to pitch today is sometimes referred in philosophy of AI as the embodiment hypothesis. And this is the idea that when we study intelligence, the body is actually a key factor, plays a role in what we mean by intelligence, and especially how we express intelligent actions. We can think of intelligence also as being externalized, for example, in our context, in expressions of sketches, design, writings. And so here's a sort of example of what we mean in the context of creativity. You have Jackson Pollock, who is clearly using his body in exploring different visual expressions and imaginations as he keeps iterating. And there are some videos of how he used to work. And it's actually very interesting when this exists to look at famous artists, how they use movement in the production and in the exploration of a visual artifact. There's another aspect of this embodiment hypothesis which I think is interesting, and I wanted to mention it today, is the link with ideas of evolution and how movement and body evolution are closely linked, and how, for example, the use of our hand has played a key role in probably influencing evolution of intelligence in humans in comparison to other primates. And linked to that is the notion of tools. Tools play a critical role in production of art in particular, but also in a sort of feedback loop play a role in putting evolutionary pressure on us in evolving this collaboration between nervous systems or brains and bodies. And then it feeds back to the evolution of tools, so we could even look at the evolution from a design perspective of these tools. Now, after this sort of high-level presentation of the motivation for this type of work, we will now focus in very particular areas of visual art production, and it will more generally fall into the area of drawings, and later we'll specialize into the sub-area of calligraphy. So what's interesting about drawing from our perspective, and so here I pitch to you a number of items. It relates, in the context of intelligent action, it relates to what we call creativity in humans. It is, from an engineering perspective, we can study it as being process-based. So it involves skills, it involves sequences of actions. It is, from a psychology perspective, it is what I call here reflexive. It is meant to be observed, to be appreciated. So not necessarily by the people who have created the artifact, but by other observers. It gives what I call an open window into our mind. So drawing is one way to explore how we think about the world, how we represent the world. And also, interestingly, it is shared by everybody as an experience. So we all, at some point in our life, experience the action of drawing, especially when we are young. Young kids learn a lot by expressing themselves through drawings. And then drawings, in this idea of an open window on our mind, reveal how their representations of the world evolve. And this has been studied a lot in, again, psychology. It is at a higher level, so as you keep progressing in the art of drawing and you become more of an expert, it has also strong influences from culture. So culturally bound notions of styles, for example, could be studied through the art of drawing. And importantly, for our discussion today, it is the type of actions that we perform with an articulated body. And I just want to give you sort of a few examples of how diverse and rich this area can be. It's not meant to be exhaustive, but here's a sketch by a famous Spanish artist, Pablo Gargalo, where we have a lot of information which is a bit fuzzy, not necessarily very precise, but by observing the result, we actually automatically, in some mysterious way, recognize objects we're familiar with. Here's another completely different example. So this is the idea of using drawings on a 2D canvas to represent three-dimensionality. Also in these drawings, there's a particular technique, which is this main line that you see through the body, called the line of action. This sort of line. So this is a technique that's used a lot in the world of animation since the 1930s or so. And it's used to, in the process of creating many different poses of a body in movement via some simple initial representation, and then you flesh out the body later on, or it's done by other people when you create many such pictures for film. Yet another completely different type of representation used in drawing, and this would be the kind of technique that you can trace through many centuries. So famous artists like Dürer or Leonardo would be familiar with this kind of technique, representation of a body, this time, or an animal, or a complex form, articulated form via the notion of primitives, some notion of primitives. And yet, just to finish with examples, also drawings can be used to capture a notion of a body in movement in time and space. So it's the notion of bringing time into explicitly into a drawing. So in terms of, I hope I've convinced you that this is an interesting area to explore, and it relates to current studies in intelligence in particular. And now I'm going to say a little more about the way we approach this discipline. So we have a sort of overall methodology, and the way we work with such an activity is to first try to understand a notion of process, which relates to skills. And usually what happens is there's a discussion between a practicing artist who has acquired a lot of skill, a lot of experience, and a scientist. That could be the same person in the best case. And some description comes out into how do you go about creating a particular type of drawing, like the previous examples, for example. Once we have this sort of overall notion that there is a notion of processes in place, and we've identified a few of them, we then we take the sort of scientific reductionist approach of trying to break it down in the smallest possible primitives. At that point, we're ready to move to a computational model. And usually we spend quite a bit of time refining these computational models, and we'll give you some examples shortly. In the more ambitious type of projects, we then move from our computational models and results and go to what I call here embodied systems, which tend to be robotic type of systems. If we achieve interesting robotic embodiment, then we're in a position where we could close the loop and start testing the models we have and try to prove whether they relate to how human, in a way, think. And this is the step where you may work with, for example, people in psychology and perception. So I'll say a little more about this notion of robots. There's other aspects of robotics that play a role here. So there is and for example, the first item relates to performance and will play a role later for artists, or how it can feed back into the world of art. It introduces a number of constraints that are not necessarily obvious when you only do a computational model. So if you have a sophisticated computer graphics model of rendering a particular style, you may not necessarily design your set of processes in the same way that when you have to actually use an articulated body to realize the same effect. So this then will have an impact on the sort of sequencing and timing of the realization of an artifact. In our own experience, it has played an interesting role, and I'll say a little more about that shortly with an example, in trying to capture notions of style. So how a style of a particular artist who is using a similar technique to, for example, render a portrait will be specific to the person. How do you explain that? One way to try to characterize that is to see the role that an actual articulated body plays in the rendering of a style, and especially in introducing uncertainties. So when you draw a particular line and you draw again, if it's a human doing it, there's usually no attempt to do exactly the same line, even if the effect is supposed to be the same. And so if you try to understand that and mimic it with a robotic tool, you may capture this notion of style. And then there's another aspect that comes into play when you have robots. You have to think in terms of control. Many parts of a robot have to be articulated. So there's all kinds of other mathematics that come into play that wouldn't be present in a usual computational model. And the first project of importance that I was involved in was a collaboration with a French artist, Patrick Tresset, which led us, after developing a computational model, to what we called Paul the Robot, which is a very simple robot with an articulated arm, an articulated eye that looks around, captures faces. The initial focus was face portrait in the sketching style that Patrick had explored previously. So very simple system if you think of robots, but it allowed us to explore some of the notions I've mentioned, including this aspect of stylistic signature. The ambition of the project was much larger than what we actually achieved, so we tried to understand all the processes that may be involved in how an artist looks at someone or has an idea of a face and then goes into realizing this face. What's important in this diagram is really that it's clear that there's a number of loops, and we should think about what's the importance of these feedbacks, and can we model and test these types of feedbacks. There's a notion of experience, looking at how other artists have rendered portraits, for example, and this would be an aspect we haven't explored at all, and probably one of the most ambitious research theme we could think of. After a few years, we ended up with a computational model, and these were the sort of last types of rendering we were producing with the computational model, and we were fairly happy with the rendering. But at that point, we were sort of stuck with the computational aspect, and if you look carefully at the details, you'll notice that this is definitely made by a machine and not by a human, and trying to understand what makes a similar drawing human-like versus machine-like was a question at the time, and the way we tried to answer it was to actually move to a robotic example. So here's a little video that will illustrate what happened once we moved to a robot we conceived of, and you can see from the motions that the robot is not very precise, not necessarily robust in repetitivity, and that becomes an interesting feature in trying to model this notion of uncertainty in every line that you put on a piece of paper. There's also all these aspects of physically interacting with a paper, a pen, which would be hard to capture with a strictly computational model, that are of interest when we move to a embodied system. So here it's sped up, but typically these drawings take about 20 minutes. It depends also of the sort of features that a particular face has, so it can be a bit longer, a bit shorter. So that mimics the real experience you would have if a human artist was drawing your producing your portrait in this style. And here's Patrick. So what happened after that is the last piece of work, of interesting work that we did together on the sort of science side was as an initial version of visual feedbacks. I didn't mention before that there's lots of feedbacks involved in the processes we've identified, pre-identified, that should be involved here. So we started to try to understand what kind of feedback could we model, and we modeled a very elementary type of visual feedback, basically using the eye to look back at the drawing as it is made and take a measure of quality of region sketch regions, and use that to decide whether we go back to that region and do a little more sketching or not. And the team of Oliver Deussen here has done much more advanced work in this area, and I think in visual feedback in the context of paintings and robots, but I think this is an area, again, for research, which is sort of one of the bleeding edges. And what happened later is that after 2013, Patrick, who used to be a practicing artist, ended up going back to the world of art, but this time taking on board this project. And if you look him up, you'll notice that he's basically on demand around the world. He has now his own studio in Brussels, and he's completely sort of went back to the world of art. So this is an example of initially art fitting into science, and then later science fitting into art. Thanks to this project, I was fortunate to meet another character like Patrick, another artist who has a strong background in computing, and in the case of Daniel, building machines is something he had already done before we met. And we decided, he knew about the work with Patrick and he got interested, and we decided that one of the next steps we could explore was studying more carefully what's the influence of movement in the quality of the traces that we can perform. And I will now let Daniel present his recent work in the last few years. I'll give you that.
Okay, hi. So I'm Daniel. Thanks for the introduction, Frederic. So as Frederic mentioned, my focus is on graffiti art rather than portraits. And when I'm talking about graffiti art, I mean this kind of drawings. So not specifically street art or figurative, but an art form that revolves around the stylization of letter forms. So specifically, and it's initially was born in New York, more or less, in the late 60s, and developed since then in an art form you can see in most big cities, also Konstanz, Berlin, etc. And one interesting fact about graffiti is that it's an art form that was born in motion. So it was born on the subway trains of New York City, as a subject that was supposed to be seen in motion, and it often involves very actions that require like fast movements and often in difficult situations. And the basic element of tags of graffiti is known as a tag. It's a signature. It's made in a way that is similar to calligraphy, and it's the building block that over which more complex forms of stylizations are built. And to create a tag, while this often might seem like scribbles to the non-trained eye, actually there is a long study of movement behind the tags. So like to achieve this type of trace that is appreciated between the graffiti artists, it takes a really long time of practice. And you have to master the movements that are involved in its production. And as Frederic said, this is a notion that we have also in psychology, in neuroscience, that we reconstruct the movement when we see a trace. And this idea is actually quite accepted in graffiti art. For instance, in the jargon of graffiti, the quality of the tag is often referred to as flow, and flow is indicative of the movement that has, the quality of the movement that has been used to create this tag. So the way in which this movement is done is quite important. So let's start with tags as the basic element. And here we see an artist from America that made an analysis of tags and identified different letters. And here you see different letters. Here are N's and here are R's, stylized in different ways. Now, if we look at the subset of those letter forms, we notice, for instance, that this subclass of N's and these subclasses of R's kind of have the same structure. So they're both capital N's, and you can describe them with a very simple structure, and the same holds for this other instance. So our approach to model this is what we call style, between quotes, let's say, as kinematics. You cannot see the title. But the idea is simple, that you have a letter form that's described with a very simple structure, and variations of style over these letter forms are described by different movements that follow this similar structure. So here is kind of an overview of the idea. And so in studying this as a research topic, I looked into in the domains of motor control and the domains of handwriting recognition and simulation. And there is an interesting field that was born in the Netherlands in the 80s, and it's known as graphonomics. And it's the scientific field concerned with the systematic relationship involved in the generation and analysis of handwriting and drawing movements and the resulting traces of writing and drawing instruments. So mainly this field went into biometric and handwriting analysis, but it has strong relations to motor control. And we can find a number of principles that are recurring in the study of handwriting, and it's been done since early 1900s till today. And it's commonly accepted that you can describe a complex trace, a movement, a handwriting movement, as a set of primitives, of simple motions. And those motions are often considered as aiming motions. So imagine that you construct a more complicated movement by superimposing many different sub-movements that are aimed at the target. And the speed, if I analyze the speed of those sub-movements, they have this very characteristic bell shape. So you can construct more complicated movements by summing those bell shapes in time. So this study led to a collaboration with a researcher in Montreal, an expert of handwriting analysis. And we used a model, I'm sorry the titles are not well visible, but a model that is known as sigma log normal model. And this model is exactly the movements as a sum of those bell shapes. And as you see, by having those bell shapes superimposed in time, you create a more smooth movement. And this is quite easy to understand intuitively, that if you're aiming at a target, and while you're still aiming at a target, you start moving towards a new target, you're going to get a smooth motion. It turns out that we can use this kind of model very efficiently and create an interface that allows you to edit motions and the resulting curves in a way that is very similar to standard methods that are used in computer graphics. The difference being that you're actually editing a motion, and the kinematics, the speed of the motion, are very similar to the ones that would result from the movements of a human. And this has advantages in our desired task of mimicking tags. For instance, you can see here that we can trivially generate a smooth animation of the trajectory by just sampling it in time. And another advantage of this is that we can use the speed to mimic the way in which ink is deposited. So we can very, very easily generate rendering effects that mimic the way in which a brush would leave paint when drawing. And this is a very simple model, but it results in quite effective rendering results. Another advantage of this method is that we can apply variations to the parameters. And basically, you're applying variations to the movement. So the results mimic the way in which, while we're drawing or writing, all our movements are always a bit different. And it mimics, we can generate many variations. So in our application, this allows us to do things like this. So mimicking, the example, a tag on a wall with an effect of spray paint, and then applying variations. And an application of this would be, for instance, in video games. You want to generate graffiti for a virtual city. You want to generate many variations from a single input that is very simple. Still in this direction, we can reconstruct existing tags. So we can take the trace of an existing tag, taken as an ordered sequence of points, and infer the movement that has generated this tag. And this, in a way, mimics the principle that Frederic before presented about us inferring a movement when we see the trace. And doing so allows us to generate variations from the input. And again, we can generate animations of the input that are natural looking, have brush effects or spray paint-like effects. And then we can edit the reconstructed trace in a way that is significant to the user. So we don't have just a soup of points that is, every point is actually signifying aiming target. So it directly relates to the motion that has potentially generated the trace. Another application of this is that we have smooth speed that we can use to control a robot. So this is an example of a work we did with Sylvain Calinon in Switzerland, a researcher in robotics. And this robot is what is known as a compliant robot. So the robot is safe, relatively safe for humans. So it means that, and we exploit this representation of aiming the movement to control the robot in a precise manner, which would be very difficult otherwise. And still with Sylvain Calinon, we went into different techniques. And this time we were looking more at the domain known as computational motor control. And in this domain, we can look at other principles that are interesting. And it's well known that when human movements are smooth, so we tend to move in a way that seems to obey some optimality principle. And it's been suggested, and it looks like a lot of the movements tend to minimize changes in acceleration or changes in acceleration, etc. And all those amounts have funny names like jerk, snap, etc. And but another fact that has been seen that, okay, it seems that we maximize smoothness, but this is more an aspect of average trajectories over experimental trials of many movements by different humans. So more recent studies have shown that actually, like, we deviate from this average smooth trajectory only when the requirement of precision is high. So this is known as optimal feedback control. So the idea is that lower precision requirements comes to reduced effort and thus a smoother trajectory. So we deviate from smoothness when we need to be much more precise. So we developed a similar approach to the one before, interface-wise. But this time the trace is generated by an optimization that balances between precision and smoothness. And this is expressed explicitly by defining those circles and ellipses that are Gaussians. So basically define a precision in space. And as you see, you can define the way in which the trajectory evolves, defining this. And this is consistent with this principle of optimal feedback control. And again, we have a smooth speed profile that allows us to create animations, as I explained before. Now, an interesting byproduct of this is that the output of the optimization is not a single trajectory, but a family of trajectories that obey those constraints that we initially imposed. So this allows us to generate variation in a more elegant way, and thus sampling from a distribution of many, many trajectories that obey the constraints defined by the user. And in a more constrained setting, we can define a form of coordination in the movement. So if we define all those ellipses to be oriented in the same way, we mimic the way in which our hand, let's say, is constrained, for instance, when we're drawing and we're constrained in certain directions. And it turns out that with this method, we can actually generate stylizations with a very few parameters, and they tend to be similar to stylizations that you will see in graffiti art. So you end up with an interface that is very easy to use and allows you to explore many variations of a stylization of a simple trajectory. And we can exploit this, for instance, in a generative setting. And for instance, here is an example of, this is more artistic oriented, but you can generate this kind of patterns by simply specifying a set of random points, connecting them with the maximum distance between each pair of points. This is known as, the inverse of this would be known as traveling salesman problem. It's kind of inverse traveling salesman problem, and you can easily generate these kind of patterns, which is fun. And another application is that we can drive smooth animation of virtual characters. Again, this has application to games. And yeah, so in this case, the animation of the body is great with computer graphics techniques, with inverse kinematics. I did the animation, and I'm a very bad animator. I apologize, but it's to give the idea. And again, we can drive different type of robots and machines with the trajectories generated to kind of mimic tags. Here is an example where is a machine that I built that draws with, wait, I'll go to that in a second. It draws with drippy ink, and drips are something that is often seen in graffiti art. This is another project that, for fun, I experiment with, is with colleagues in the Netherlands, and it's a machine that spray paints on the floor. And again, we are controlling this with the curves generated by the methods I showed you before. So now, from here, okay, so as I said before, graffiti art is not only tags. Tags are the basic element. So lately, we've been collaborating with Paula Zente and Jose Echevarria in Adobe Research, and we have done some research on trying to develop similar interfaces for generating more complex forms of graffiti art. And here you have an example of a person tracing graffiti art to see. And as you see, the motions followed by the artist, here's another video, for instance, are actually similar to the motions used in tags. In fact, tags form a basis not only for the construction of graffiti letters, but also this hand style in which they're executed is an imprint of the person in his style in more complex forms of lettering. Another thing that we can notice is that the way in which those letters are composed is kind of an abstraction of 3D, a mix of 3D and 2D that is not easy to achieve with the traditional computer graphics methods. So you see you have layering of letters, you have overlaps, 3D-like effects, but this would be kind of difficult to achieve with the traditional methods that you have in a computer-aided design setting. So again, we follow a similar approach, and we have a simple structure. This time, instead of generating motions, we generate primitives, simple shapes that we combine over the structure of the letter form. And here is an example of what we do. So here is a simple stroke defined by those points. And to generate a stroke, we generate a polygonal representation. And then we create a motion with the methods we showed you before that follows this very simple polygonal representation. And this allows you to generate many different stylizations over this, what we usually would be a geometric stroke. And depending on the way in which we follow this basic shape, we can generate different types of strokes. So let's say we can generate two motions on each side, so you will have a kind of square-ended stroke, or you can make a periodic motion that will make a fully smoked stroke. And we then develop a method in which you can interact with this stroke, and you can define which parts overlap, which parts go forward, which parts go backwards. And this is fully 2D, it's not 3D, so it's kind of an imitation of 3D, but with a very, very simple user interface, which allows us to mimic this kind of this kind of effects that are similar to graffiti art. So this results in an interface that is similar to one I showed you before. And it allows a user to quickly create graffiti letters. And for instance, yeah. So usually doing this with the traditional methods would require you to cut parts, to put one part behind, put one part in forward, or in 3D to define a very complex 3D projection that would make it hard to make more abstract effects such as those. And again, this can be exploited for more generative applications. So here you see a very simple grid. So imagine you have a vertex at each point, so you have what's known as a lattice. And if we connect, we make a path over this lattice and create one single stroke and define overlaps that intertwine, we can generate these kind of patterns. So this again is an example how generating this kind of representation that is higher level allows us then with a very simple input representation to generate complex patterns that are resembling to graffiti. This is other examples, so if you start shifting things, we can get examples that are very similar to more complex forms of graffiti art. Etc., etc., etc. And a nice, again, a byproduct of the method we develop is that it generates traces that are consistent with the way in which you defined the strokes as an input, which means that you can again take a machine and simply send the paths generated by the system, send them to the machine, and the machine will make the drawing in a way that is actually pleasing to watch and makes visual sense. This can be improved a lot, but it's just directly computer to machine without any pre-processing. Yeah, and here this is not a complex robot, this is what is known as a plotter, so it's a simple 2D machine, but it allows you to draw also on notebooks on any surface easily. Yeah, so that's it. So if you have questions, yeah. Yeah.
Yeah, I have one question about the materials that you're deciding to use. Like because you said you're coming from graffiti art, and then usually you actually work then with a spray can.
Yeah.
But with your robotic works, you're actually working with pen and
Yeah.
much more controlled element, let's
Yeah.
say. Although, so why the decision to work right now with pens and not actually to work with different materials?
There's two facts here. One I forgot to mention, that I'm simplifying things, and often when you practice graffiti art, you start from a sketchbook. So your practicing is on paper. So I'm actually currently mimicking this, and I'm not, I didn't look at spray paint, I didn't try with a robot with spray paint, but I would love to. But actually I don't think it's much more hard to control. I mean, it has much more degrees of freedom, so you could have much more freedom in creating effects, so you could have orientation in the way in which you spray, and actually that's a limitation for our current work. We're not considering that, so we're always considering a point movement. But it would be something I would love to do in the future.
So like your movement now is more about the trajectory, but you then less look about like the pressure and the speed, because those elements will be much more evident with different materials.
I'm not looking at pressure, for instance, in the example I showed before with the brushes. I can go back. That's a very simple, very, very, very simplistic model of pressure, let's say. So the assumption is that when you move faster, you have less pressure. And it actually turns out to generate results that are okay looking, but it's not realistic. So yeah, we're just considering the point movement at the moment, which simplifies the problem, but it's good to start from simple. Yeah. Yeah.
More questions? Do you build a model of each letter separately?
No, in this case it's interactive. What you saw here, it's a user clicks So you could have a library of letters and use those. And we're working, it's like work in progress, we're working in extracting structures from fonts or from existing letters to stylize those later. But it's complicated. What? Currently, we're not using deep learning, no. So actually, that's an interesting fact. That's interesting. I mean, that's my idea that I would be interested in using deep learning, but using it at a higher level. So using it with those simple representations rather than at a very, very low level. So not generating letters from scratch with deep learning, but generating them at a higher level once you have the structures in place. That's kind of the direction I'm going in. But
and we have one paper on this type of thinking.
yeah.
So if you're interested, we can point you towards that.
Yeah.
It's based on a recurrent neural network, so it takes in consideration the fact that it's time-based, sequential.
So instead of imagining, every single point, every single sample from the trajectory, you consider just the primitives. So instead of having, I don't know, hundreds of thousands of points, you will have 10, which simplifies the representation a lot. Yeah.
Yeah, I have a related question. Now, if you try to mimic an artist, a graffiti artist, I think the good thing of your modeling is that you can reduce it to maybe some simple forms of how this artist uses his motion to create the artwork. So you would, in theory, be able to learn from some artworks. Maybe you record not just the artworks, but the ways of how the artworks were created, and then you should be able to mimic his way of doing.
In principle, I'm interested in seeing actually how you might be able to, with a simpler representation, I think we have to do tests, so it's just a hypothesis, but you might be able to do it also without deep learning, with very simple models, so an HMM or like...
Just learn from this, how he uses his muscles to create the forms. Yeah.
And another fact that currently, like a lot of these aesthetic results are driven, that's very non-scientific, but they're driven by my aesthetic taste as a graffiti artist. So I come also from a background as a graffiti artist. So some of my work I'm just evaluating and saying this is good graffiti, this is bad graffiti, and it's personal, So like, you might not agree with me, and you might think that, okay, this is bad, this is good. But then again, if you develop an interactive interface, it's up to the user then to evaluate their own work, and it allows enough degrees of freedom to allow interaction for different artists. Yeah.
There's another time-related dimension to gravity, and I was wondering whether you reflected on that. It's usually if like graffiti artists work in the field out, they have a limited time span.
Mm-hmm.
Yeah.
So that's to say it's risky, and of course it's higher evaluated if it's more risky, and so on. And riskiness is defined by the time span you have before police catches.
Yes. Yeah.
So now this is something that obviously goes into the production of the art itself, because it means how much can you produce within a given period of time. Is that somehow going into your reflection of simulation, of simulating?
No, absolutely. In two ways, no. So in one way, I try to separate graffiti as a live action, as a life experience or lifestyle or whatever, from simulating the style aesthetically. So, but at the same time, I think these factors you're talking about influence the way in which graffiti has evolved aesthetically. But that was the point I was trying to make at the beginning, that I said that it's art in movement. So it was born on trains, being seen in movement, but also it's an art form that is made in movement, like running and trying to be in a place for a very short time. And
Exactly.
this is another aspect of movement that is not really simulatable, though, I think. It's
question is whether it might actually have an effect on the forms produced. That was.
I think definitely, yeah, that's my point. I think it has in the long term, the evolution of graffiti has been dictated also by that. So by the necessity to move fast. And that's maybe what
cannot be modeled, this part.
I'm kind of modeling the end result that is a kind of optimal movement. Yeah. And I think that it has many implications, but I'm not really going into those. But I think at the end of the day, like, I think this has led to the appreciation of movement maybe in graffiti and the importance of the quality of movement, because you have limited time, you're under pressure, so the higher the quality of your movement is while still being under pressure, the better it is considered, and that kind of makes sense, I think. Yeah.
And there is research with one of our collaborators in graphonomics, Professor Plamondon, where we've noted, we're not involved in that aspect of research, but they have results that show that you can use the kind of models we've used to detect or represent expertise in tracing. So this has been studied mostly in signature, but so you can notice the way a signature evolves and becomes sort of stable. So you start reaching sort of stable state where you're not thinking and it flows. But then you can also notice when you start moving away from that, and it tends to be, for example, aging, or maybe they're actually studying using these models to try to detect whether early signs of heart problems or trembling, etc. Mm-hmm. So this notion of the way I would relate to your question is that graffiti artists who become experts and want to do something more risky, they actually have to practice a lot and get really good at becoming very good from a kinematics point of view. And those kinds of models probably at least give us a way to try to study that and sort of compare naive or maybe a risky situation. I don't think anybody has done that kind of study this way, but we could probably address that issue here.
From the movement component point of view, is like the more you're expert, theoretically, the less movement components you use. Mm-hmm. So yeah. So if you're hesitating, you will have a lot of hesitations and many peaks in your speed, and and you can analyze that. Yeah.
I think there was another question.
One question related to yours also. So far, you have basically an end result encoded, and then you produce that. But what about like introducing improvisation to that? So like a feedback loop of, okay, I made this stroke, and I go there. Now I observe that, and basically, every stroke would create another improvisation or another.
Yeah, I would love to do it, but it's.
Go about like.
The idea is building kind of an infrastructure over which you can build those systems in a simplified manner. So once you have those components that you can combine to generate interactively or with very simple representations graffiti, then I would like to eventually explore also feedback systems like that. But it's like building blocks. So I'm a bit far from that still. Yeah.
The graffiti artists usually have hundreds of sketches, and then they found which one is the best. As you said, there is a good graffiti for the artist, and then there is bad graffiti for that artist.
Yeah.
And then can the machine also choose which one is the good graffiti, which stroke was the best angle, or the speed, or the structure that it created by itself?
My system currently no, but it would be nice. Yeah. No, it's also an interesting research to do.
I think at that point it's good to have collaborations with psychologists. Yeah. So we have a collaboration with psychologists at Goldsmith, who are not addressing your question, which sounds quite ambitious, but are studying the impact of producing variations with this kind of interface, and noticing how humans react and try to give a quality back in terms of what's the outcome, and whether we can see a correlation between what many humans will say and the way we've controlled the models. So they don't know about the models, they don't need to know. But that's the kind of study you need to do, I think, but you need to engage with another discipline, so this is beyond what we can do ourselves.
And again, it's a very, very small steps. So it's like we're doing some studies, but it's like very, very early and it's very methodical. So we're starting with very simple traces, and eventually we might build up to, you know, the kind of things you're proposing, but it's very far from here, yeah, still, yeah.
I was just inspired to the question that this there's maybe a bit going beyond the framework of this meeting here, but maybe you know something about that, or maybe you're thinking about something. If you describe or formalize graffiti in this way, then there might be a way of having a similar description for breakdance as a kind of transitory, flowing graffiti. So it might be kind of a similar kind of stuff. Do you know any studies about that?
No, but there is definitely relations, I think.
Yeah.
Historically speaking, yes.
Yeah, and also the idea of optimal movement, but it's complex because it's a whole body in this case. But
it's true, yeah, three-dimensional.
But I think there is
it's like three-dimensional, not archived graffiti, or the other way around.
Yeah, it's actually I didn't talk a lot about that, but it's also interesting to look at graffiti. Graffiti is interesting in two senses also, because it's in a way sampling at the visual level, and that's related maybe to the more musical side of hip hop. And you can see influences of design on graffiti at the same time in which it was produced, and certain styles were influenced from design in their given time. And nowadays you can see influences of graffiti on design, so there is this kind of influencing. But the most interesting part, I think, is how different visual cultures kind of contaminated graffiti and the styles. There is a really nice book about that I can suggest you if you're interested.
Yeah. I'd be interested in that. I think there are many more questions that we can discuss now when we go over to the place. They will be around. But before we do that, Liat wants to tell something a little bit about what we see there.
Yeah, I'd like to close this. First of all, thank you very much for the very interesting.
Thank you for inviting.
In a way, link very strongly to the exhibition that we have here right now in the library, where we actually start looking again at painting as a matter of fact and a matter of movement, but in a way going a bit beyond of the physical limitation of an individual person. So the work that you can actually see here generate strokes. The robot is always generating strokes using a calligraphy brush. So the calligraphy brush itself has a very strong deformation that happens from every pressure after every strokes. And those differences give us a very new feedback back. So when we actually looking at the strokes, we kind of guessing it looks very gestural, it looks very fast, but the velocity is fairly steady. And so it's like we're actually seeing how one can imitate things that look like they actually created in different kind of movement. And the second is actually the location of the stroke. So Frederic gave before the nice example of Jackson Pollock, who actually exactly created, like the entire painting is a record of its own movement, but as well it's something that limited to his own body. Every stroke, so every line that he makes is related to where he actually was standing before. And in this case, we're trying to kind of go beyond it. While the strokes are being generated, here is information taken through the movement of visitors that walk through the quarter hall here in front of the Bib Cafe, giving us kind of a new arrangement of like why I make first a line here and secondly a line there. Can we actually see there is a logic or there isn't a logic that's going in there? So what the exhibition here is trying to create is to open a studio situation. Instead of looking at a painting as a flat image of something hanging on the wall, we open it up into a live performance of the robot, creating the works. Each work that you see hangs is done during the days over the last 2 weeks. In the beginning, all the frames were empty. And if you look closely on each one of the works, there is actually a time and a date showing the movement that actually happened during the time. Every 15 minutes we moved the paper. There is actually an automatic paper move that happens, but because of the limitation of the paper, it was ripping very easily because it was still wet. We done it automatically, so there is a lot of the limitation of the medium itself. And this is all combined with a video work that gives you kind of a slow motion on how the ink is actually working on the paper after we apply the paint. So there is so many different levels that give us the finished visualization that we see. And this question about control and losing of control in the creative process, especially when we're working with computer and with robotics, what one thing's supposed to be very precise and clean. We have situation here of, can I really predict this? How much can I really predict of what is going to come, and how we react in working with this as an interactive tool and not only as autonomous machine in different ways. So if you have more questions, I'll be very happy to answer. Or Marvin is here too. He's going to operate the robot right now and can give more technical explanation of how the program is running and how the elements comes together. So yeah, please join us. Thank you very much.